We're moving on now to our next topic, which is the conservation laws. These conservation laws, they're actually the fundamental equations or governing principles in the study of mechanics. And that includes the solid mechanics. Let's write it here, conservation laws. Okay, as I've said, they are governing equations or governing principles, governing equations in the study of mechanics. And specifically, these are conservation of mass, then the conservation of energy, then the conservation of momentum. Let's discuss this one by one. Well, the first one, we have the conservation of mass. So for the conservation of mass, basically what it means that mass is conserved. From the word itself, it means that mass is conserved. Let's try to draw this in picture. If we have this conduit, a closed conduit for fluid flow, let's say we have an arbitrary shape, and this is the center line. What it says basically is that the mass that enters, let's say this is our point 1, our entry point, and this is our exit point, and we have a flow in this direction. So this conservation of mass basically says that the mass that enters the system, and let's say this is our system bounded by this point 1 and point 2. Now the mass that enters the system is the same mass that exits the system. And that's for a steady flow conditions, meaning that the properties doesn't change with time. So for example, the mass, if the flow is steady, then the mass flow rate going into the system is the same mass flow rate that goes out of the system. But if we have a non-steady flow, and let's say we have higher mass input here, or mass flow rate in, as compared to the mass flow rate that goes out. So if you have higher mass input than the output, then of course you will have an accumulation inside the system, right? So if we draw it here, for example, we have a container and we try to input, let's say, water. And if we have also an exit right here, a tap, for example, except that this input is higher or is greater than the output, then of course we will have an accumulated. Okay, so for example, we have an initial height of water. Now if you have higher inputs flow rate, then of course you will have an accumulation inside. Now in the same way, if you have higher output compared to the input, then of course you will have a lowered or a decrease in accumulation or decrease in the storage. Okay, so mathematically we can write that the mass flow rate, by the way, that's m dot, denoting that this is mass per unit time because we're talking about motion, we're talking about fluids that flows. So we have per unit time. So m dot, that's the mass flow rate entering the section 1, that's the m in, minus m out, the mass flow rate exiting, is just equal to the rate of change of mass in the system. And if this is a steady flow, then of course this will be 0. There's no change in the There's no rate of change in the system, and therefore you can write that M in is just equal to M out. Now let's talk about this mass flow rate. This mass flow rate is actually given or expressed in this equation, that it's rho A times the area times the V. And that's the velocity. Okay, so this is velocity. This is area, cross-sectional area, or area perpendicular to the flow. And this one be the average velocity across that cross-section, and this one is the fluid density. Okay, so this is the equation for the mass flow rate. Now let's check the units. Now the mass flow rate should be in kg per unit time, so kg per seconds. Now this is density, then we have a unit of kilogram per meter cube. Then the area, that's meter squared. All right, and this one, the velocity is meters per second. Okay, so if since we have m squared and m in the numerator, and we have m cubed in the denominator, then we can cancel this out, and therefore we can have kilograms per second. Okay, so that's the mass flow rate. Now, how do we know that that's the equation? Okay, recall that mass is just simply equal to mass is equal simply to the density times the volume, right? So now we have the same symbol for volume and velocity. Now let's write, if we are talking about volume, let's put a bar right here, okay, to denote volume. So this is the equation for the mass, density times the volume. Okay, so what's the volume? Now if we consider an element right here, fluid element, okay, so we have this area, right? We have this area and we have this length. Now let's say our length is S or delta S. That's delta S because it is in motion. So this is our point 1 S1, and this is our S2 after some time, right? So that's delta S. So that's the displacement from point 1 to point 2 in this fluid element. Now since we are referring to rate of change of position, then that's gonna be translated to delta S all over delta T. So displacement divided by time, that's just velocity. Okay, so therefore if we substitute this velocity and acceleration here, then that's gonna be rho A times the velocity. Okay, and that's gonna be the mass flow rate. So that's m dot, and this one should be m dot as well, because we're talking about fluids in motion. All right, now for our equation, says here that m dot in minus m dot out, okay, is equal to the rate of change of mass in the system. Now if we have a steady flow, then this is 0, and therefore m in is equal to m out. Now if we substitute our expression for the mass flow rate, then that's going to be rho A1 V1 is equal to rho, right? Let's write rho at point 1. Then this is our rho at point 2, A2 V2. And for incompressible fluids, that means that the density doesn't change, because there are also flows wherein density changes. So if our case is that we have an incompressible fluids or the density is constant, then this will be equal to 1, and therefore A1 V1 is equal to A2 V2. And this expression is what is called, or what is known as, the continuity equation. Okay, so that's the area times the velocity at point 1 is just equal to the area times the velocity at point 2. And if you check the units, we have actually a unit of meter cubed per second. Right? This is meter squared times meter per second, and that's going to be meter cubed per second. And this is what is called as the flow rate, or the volumetric flow rate, or also referred to as discharge. And for this parameter, commonly what's used is the big letter Q for the flow rate. And of course, if you can express this in terms of the volumetric flow rate, then of course we can also express this in terms of the weight flow rate, or the mass flow rate. Now, if we try to consider, let's say we have a conduit right here, and then we have also another pipe or conduit that's joining in this main pipe. Then of course, and let's say this is our flow, this is our another flow, then this will be our exit, right? This is inflow, and then outflow. Then it says here that the mass, based on this conservation of mass, that the mass in is just equal to mass out, right? So if you have many entry points or many exit points, then we can rewrite that as this as the summation here. Okay, so just remember the main idea, that the mass inside the system, or the mass in the system, is conserved, and that means that the mass in minus the mass out is just equal to the rate of change of mass. And if we have a steady flow condition, this is 0, therefore this is the resulting expression. And if we substitute the equations, then we got this A1 V1 is equal to A2 V2. We neglected this density. It's because if we consider incompressible fluids, then the density doesn't change. That's why we have this A1 V1 is equal to A2 V2, which is referred to as the continuity equation. Okay, and this A1 V1, if we check the units, that's m cubed per s. That's the volumetric flow rate, and this is also referred to as the discharge. The unit is big letter Q. All right, now we'll do problems regarding this mass conservation. Okay, so for our problem number 1, we have the inside diameters of the pipe. The inside diameters of the pipe at section 1 and 2 are 50, this should be 50 mm, 50 millimeters, and 100 millimeters, respectively. Water at 70 degrees Celsius is flowing with an average velocity of 8 meters per second. So here we are already given the data of the unit weight and the mass density at 70 degrees Celsius. Okay, so here our unit weight is 9.59, and that's lower as compared to the commonly used values, which is 9.81, simply because this is actually affected, the density is affected by the temperature and also affected by the pressure. So at 70 degrees C, we have a lower density. Okay, so this is our figure. We have an arbitrary pipe. So this is our point 1, and we have our point 2 right here. So our point 1 has a smaller diameter, and point 2 has a bigger diameter. And we are asked to find the velocity at section 2. What is the velocity here? and what is the volume flow rate or the volumetric flow rate, what is the weight flow rate, and the mass flow rate. By the way, this problem is taken from the textbook of Mott and Antenner. That's example problem 6.4. Now, by the way, going back to our previous paper, we see that A1 V1 is equal to A2 V2, which is just simply our discharge Q, and that can be written as Q sub 1, the flow rate at point 1 is just equal to the flow rate at point 2. Okay, so here in our problem, in our point 1 we already have the diameter, and our point 2 we have also the diameter. Okay, so we can write it here. So for our given data, at point 1 we have our diameter is equal to 50 mm, and our we have here, okay, so water at 78 degrees is flowing with an average velocity of 8 meters per second. Okay, this should be at section 1. Okay, so our velocity 1 is 8 meters per second. And for our point 2, we have a diameter of 100 mm, but we don't have the velocity because that's what we're actually solving for. Okay, so here we can see that the diameter is actually related to the area. The from the equation A is equal to pi d squared over 4. Okay, so if we have the area, we have the velocity, then we can solve for the flow rate. Now, if we have the flow rate at point 1, then that's the same flow rate at point 2. And if we have the flow rate at point 2 and we have the diameter at point 2, then we can solve for the velocity at point 2. Okay, so our step number 2 is to solve for the flow rate for the Q1. So writing now our equation, Q1 is equal to A1 V1 is just simply pi d sub 1 squared all over 4 times the velocity at 1, and that's just pi times 0.05, because we have to convert that to meter. 0.05 squared all over 4 times the 8 meters per second. Okay, and therefore, if we do the calculation, what we get is 0.0157 meter cube per second. Okay, so since Q1 is equal to Q sub 2, we can now solve for velocity at point 2. Okay, so our working equation, Q2 is equal to A at section 2 and velocity at section 2. So therefore, the velocity at section 2 is just simply our discharge at section 2 divided by the area at section 2. And this is 0.0157, and that's meter cube per second. And here we have our area, just pi d. So again, we have to convert this to meters so that we'll have a consistent units, and therefore our velocity at point 2 is equal to 2 meters per second. Okay, so this is our Q1, which is just equal to Q sub 2. Alright, so we now have Q1, Q2 velocity, and we have also the area. Now, you would notice here that our velocity at 1 is 8 meters per second, while the velocity at 2 is 2 meters per second. Okay, so we have a difference in the velocity. Okay, this one is faster, this one is slower. Okay, so in order to actually obtain the same flow rate, now it has to go slower because the cross-sectional area increases. Therefore, based on the equation alone, we have this Q is equal to AV, right? So we can also write A over V, and we can see that if this is constant, then we can see that the area is inversely proportional to the velocity. Okay, so if this is larger, then of course you have a slower velocity. If you have a smaller area, in order to get the same flow rate, then you have to go faster. Okay, so this is our relationship. Again, please remember this is for a constant flow rate. Okay, now let's move on. Let's solve for the weight flow rate because we already have this volumetric flow rate. So for the weight flow rate, solving for weight flow rate. Okay, so weight is just simply our discharge times the unit weight. So this is 0.0157 meter cube per second times our unit weight, which is 9.59 kilonewtons per meter cube. Okay, so we have meter cube in the numerator, and here we have the meter cube in the denominator, and therefore we can solve, and we'll have 0.151 that's kilonewton per seconds. And for our mass flow rate, we have the mass is just equal to the discharge times the density. Okay, so 0.0157 meter cube per second times the mass density, so 978 kilograms per meter cube, and therefore we'll have a unit of kilogram per second. So this is 15.35 kg. Okay, so just a brief recap on our procedure or steps. Now, we first analyze the situations. So we need to have the area or velocity or discharge. I mean, we have to have at least two properties in order to solve. Then in our analysis or in our investigation, we see that we have the diameter at point 1 and velocity at point 1, but we don't have the velocity at point 2. So since we have the same flow rate, then if we solve for the flow rate at point 1, that is the same flow rate it would be exiting at this point 2. Okay, so we first solve for the flow rate Q1, which is equal to Q2. Then we solve for the velocity at 2. Then we solve for the weight. Actually, we just converted this, the weight, and then in terms of the mass flow rate. All right, now we'll do another problem regarding this conservation of mass or the continuity equation. Okay, the next problem, we have a pipe of 20 cm diameter. It says that it is carrying a discharge of 0.1 meter cube per second. If the diameter is reduced to 5.0 cm at its end, calculate the velocity and velocity head at the pipe outlet. Okay, so this is our pipe because initially we have a 20 cm diameter, and the problem says that if this is reduced, okay, so if we have a reduced diameter right here at the exit or the point 2, then what is the velocity? What is the velocity at this point 2, and what is the velocity head? Okay, so by the way, this problem is taken from the textbook of Cruz et al., and that's example number 5.1. Okay, so for the solution, now again, our assumption is that this is an incompressible fluid and that this is a steady flow. So we have, okay, so an analysis or given. So we have diameter at 1. Diameter at 1 is 20 cm, and we have Q1, the discharge with 0.1 meter cube per second, and what else? At point 2 we have the diameter of 5.0 cm, and we are asked to find the velocity. Now, since we have the same flow rate, right? Since Q sub 1 is equal to Q sub 2, then therefore Q sub 2 is equal to A, area at section 2, times the velocity at section 2. Now the area is just simply pi d squared, so 0.05, oh sorry, this is 0.05, right? 0.05 squared over 4 times the velocity. Okay, so this is what we are actually finding, and our Q sub 2 is just equal to Q sub 1, which is 0.1. Right, so therefore V sub 2 is equal to this is equal to 50.93 meters per second. Okay, and then number 3. Okay, solving now, since we have the velocity at point T, then we can solve now for velocity head. So V squared over 2g is just simply 50.93 squared over 2 times 9.81. Okay, so this is meters per second, this is meters per second squared, and we'll get a value of 132.2. That's gonna be meters, right? V2 squared all over 2g. Okay, so just a brief recap on our procedure. Now, we first analyze the problem, and we can, from there, we can actually find, or we can actually figure out which parameter or which equations to be used or can be used directly. Okay, so the first thing that we observe is that the Q1 is the flow rate is given, and since Q1 is equal to Q2, therefore you can solve for the velocity. Okay, so since we have the velocity, then we can solve for the velocity head, and we just substitute the value of velocity and we get a value of 132.2 meters. All right, in the next video we'll do another problem regarding this mass conservation or this continuity equation, and then we'll move on to the conservation of energy.